Here's a little help for homework 4, covering digital abstraction, essentially combinational logic. So there's 3 problems in this set, and I'm going to say something about the first problem and the third problem. So in this first problem, you are given what is called a 4-input multiplexer. So the way to think about this is that if you had a rotary switch that could rotate and touch any one of 4 inputs, A, B, C, D. Okay, basically you would be passing one of those inputs and only one of those inputs on to the output Z, and which output would be passed on would depend on the position of the switch. And what determines the position of the switch are these select bits. Okay, so I made a truth table here with, there's actually 6 inputs. There's the 2 select bits, S0, S1, and then there's the 4 input signals, A, B, C, and D, and then the output, Z. Okay, now that would be, so because you have 6 inputs, you could say, well, we have a total of 2 to the 6th, 64 inputs. We don't need to create a truth table like this. So let me show you how you do this. So for the case of S1, S0 being 0, 0, like right here, it says, okay, A is selected if S1 and S0 are 0. So what we'll say is if A is high, then Z is high regardless of what B, C, and D are. Right? Furthermore, you can even write this shorter by saying, instead of writing a separate line, you could say if A is low, then the output is low. Okay? So in this way, you really only need to write 4 lines. You'll fill this out for each of the select bit combinations. So that should save you writing out a huge truth table. Now if you were doing a sum of products expression, okay, Z equal sum of products, you might wonder, how do you express this first one? Okay, well, I'll give you a little help here with the first entry. So S1 not S0 not, okay, and then the output at that point will be true if A is true and false if A is false. So okay, the one term that produces the one entry that produces a true output that's dependent on A is going to be this case right here, S1 naught times S2 naught, S0 naught times A. This will be your first entry. All right, I want to tell you a little bit about this 4-bit adder, problem 3. So let's do a little decimal arithmetic. Okay, suppose that you want to add 18 and 14 together. Right. So when you add these, 4 and 8 is 12, and we carry the 1, right, and add that to these other 2 digits, so we get 32. Right. This here is called, I should say this piece here is called a half adder. So the idea is that you have digit 1 and digit 2 that come together, you add them, and you get the sum that comes out, but then you also get the carry. And that works fine for the ones position, but for the tens position, you need to have a carry in, right, from the ones, and you need to have a carry out to go to the hundreds. So a full adder has digit 1 going in. Maybe we'll write it more generally here. Digit 1, digit 2, and then it'll have a carry in, and it will have a sum coming out and it will have a carry coming out. Okay, so for instance, if we were adding the numbers 246 plus 155, right? Then we would do 6 plus 5 is 11, and we'd carry 1. And then we would have 4 plus 5 is 9 plus 1, and we'd carry 1. Okay, so implementing this adder here, okay, implementing this is digit 1, this is digit 2, this is carry in, and this is carry out, and this is the sum. Okay, so those correspond to these guys here. So that's the idea. And if you have one, this is called a full adder. Let me write that. So this is a full adder. Now, if you have a full adder, you can take two full adders and put them together to make an adder, a full adder that can handle two-digit numbers, right? So we could take the output of, we could take the carry out from, if this is the ones, right? This is the, let's say this is the tens column. We could take the carry out, take that into a carry in for another block, right? And we could use this to implement the hundreds and so forth. Okay, so you're going to produce a 4-digit adder, right? Which would be like ones, tens, hundreds, thousands, but it's going to be binary, not decimal. Okay, so let me do a half adder, half binary adder. Okay, so we have inputs, call it A0 and B0, and we have the output S0, and we have a carry out 0. Okay, so we have 4 combinations on the input, right? And so 0 plus 0 is 0, and the carry is 0. 0 plus 1 is 1, carry is 0. 1 plus 0 is 1, carry is 0. And 1 plus 1 is 10. So this is the key one here. 1 plus 1 is 10. So we have 0 for the ones position, and we carry 1. Okay. Now you're going to draw a schematic of this, right? Using nots, ors, ands, and then I've also told you can use exclusive ors. Okay, and just to show you this right here, look at S0. It's true only if A0 or B0 is true. So this is really just an exclusive OR. Okay, so it's very simple. You can make up, basically you'll draw a block of a half adder, put your gates in here, whatever you have, and there will be 2 inputs, A0, B0, and you'll have a sum that comes out, and you'll have a carry. Right? That's a half adder. Then you have to consider the case where you would have for a full adder, right? We can't chain these together to do ones, tens, hundreds, thousands unless we have a full adder. So we need to augment this first one. And it will have an A0, a B0, a carry in of 0, and then it will have the sum 0 and the carry out 0. Okay, that's a full adder. And that is step 2, full adder here. Now, I say you will, let's see, draw a schematic that shows how to connect 2 half adders. Plus, and I didn't mention this, plus you'll need one other logic gate. One other 2 input logic gate. All right, such as like an or an and, something like that. Okay, so it's going to take 2 half adders and a logic gate to make a full adder. All right, and once you've produced a full adder, then you can put 4 of those full adders together to produce a 4-bit adder. Okay, it'll take 4 of these to produce a 4-bit adder. And in this case, you're not asked to draw the gate level schematic, just draw a box, just like I've done here for the full for the full adder, and put 4 of them together, wire them together to implement a 4-bit adder, having a carry out. Okay.